Hi everyone and welcome to the computational chemistry tutorials for beginners. In a previous video we covered the concept of energy minimizations in computational chemistry and why do we need it before performing a molecular dynamics simulations. And at the end of the video we give some examples of the available algorithms that can perform energy minimization. And one of the most commonly and famously used is the Steepest descent, and also called gradient descent algorithm. So today quickly we will cover the basic concept of this algorithm and how does it work. But before I go, what does algorithm mean? Algorithm means you set some rules or path to convert an input into an output. So by definition, it's a process or set of rules to be followed in calculation or even solving a problem, especially by computers. So that's why, people always connect algorithms to computer, but algorithm could mean something can be performed by yourself. It's my algorithm in working is follow this path, okay? But now we are interested in computers. So in computer, we put some rules to convert an input into an output. And Steepest descent or gradient descent is an optimization algorithm. And it's used to find the local minimum of a differentiable function. And what does optimization mean? Optimization is also called a mathematical programming. It's a process of choosing or selecting the best element from a set of variables based on a criteria. For example, to find the local minimum of a function using this algorithm, we take some steps or we choose some variables proportional to the negative gradient of the function at the current point. I don't like definitions, but you will understand what I mean later. So this is the definition of the Steepest descent. It's very basic. But before I go on how it works, let's understand two important concepts. The first one is, what does energy function mean? Energy functions, it's mathematical functions that calculates the energy of a system based on its state. Its state could be what? Could be its coordination, its position, its topology in the space. So when its state changes, the energy is going to change. If you have a system at a specific coordinates, change it so its energy changes. So now we can calculate its energy based on this on this function. The second concept is the potential energy. From basic physics, the potential energy is the energy held by an object because its position relative to another object. So that guy is tracing his arrow in this way. So it has the maximum potential energy. And another definition, potential energy is the energy stored in a system or an object due to some stress, or it's due to its position compared to another object. For example, because we are interested in proteins, this nice figure of protein, it's a three-dimensional structure because it has some potential energy due to some intermolecular interaction between its atoms. It doesn't like to stay in this way. If I'm talking about its folded state, it does like to be in this way because of some interaction. So to reach this folded states, proteins move in some very complicated way. It's a paradox to reach this lowest potential energy possible. So now it's in a folded globular state. So now this protein has a potential energy, okay? The third concept is the potential energy surface. So now we learned what is potential energy and what's energy function. So a potential energy surface, it's a kind of potential energy function. It's a description of the energy of the system based on its state, based on its coordinates. And the simplest example for this, which is not about protein, it's about the hydrogen molecule, which is composed of two atoms. If we want to describe the covalent bond between the two hydrogen atoms, we can represent it as a function in the intermolecular distance. It's R. For example, at a distance very far from each other, the energy of the two atoms will be stable. They are not sufficiently close to interact, so it will stay somehow constant at this process. But the more you bring them together, they start to be attracted to each other to form a bond. To form a bond. So you bring them together, they become more comfy, and the energy decreases up to some point. And when you force them together, of course, they have electrons, and this electron we're gonna start repulsion process, and then they start the repulsion process is going to start, and then the energy is going to be pro high because they don't like to be in a close contact. So it's like, come close to me but keep me my private life. Okay, so this is a very basic of diatomic molecule potential energy. But for proteins, it's going to be very, very complicated compared to this, because here you have only one interaction, but in proteins you have van der Waals, you have electrostatic, you have hydrogen bond, you have hydrophobic interactions, you have many of interactions that define this curve. The curve of proteins is not going to be in this simple way, or it's not going to be a very simple function. For example, this is the more complicated. I'm talking about the folded and unfolded state of protein. The protein, it's in folded state, it's going to have a low potential energy, but it's in unfolded, unstable, the potential energy is going to be very high. So now we are seeing that chemistry became somehow geography or topology, because in simulation you're going to listen to the word topology files, atom types, space.this. So since we are changing coordinates in space, so it's becoming like a surface, it's a potential energy surface. Okay, so proteins are going to be somehow in this way, and we're going to sample some calculations here and here, folding and unfolding simulation and blah blah. So this is called the potential energy surface, and why it's important in computational chemistry. How does it work? It's very simple. It's just kind of cycle. Okay, imagine that this is the potential energy of the protein I want to minimize. So the first step is I start at, I guess, the initial coordinates. But in proteins, we already know the initial coordinates from, if we are talking about a crystal structure, we already know the initial coordinates. But if I'm working on Ab initio stuff, so you guess the initial coordinates, and let's call it Ri, okay? Then we compute the change in this function. I forgot to tell you, this is the potential energy, and this is the R, the coordinates. Here in one dimension, but it's R in X and Y and Z. So the change where R is changing the coordinates, is changing the potential energy is going to change. So as I said, we first have the initial R, the initial coordinates, and then when we compute and calculate the change in the energy, which call it delta V, with the change in the coordinates, and then we update our coordinates. We call it Ri plus 1, which equal to the initial coordinate minus some scalar gamma multiplied by the gradient, or the change in the energy. Okay, this is the scalar which determines how fast I'm going during my optimization process or my minimization process. Okay, so first you have initial, then you change the coordinates, so, and you compute the change, the new energy based, or the gradient in energy based on the new position, and then you check at the end of the cycle, you check if this is converged or not. And what I mean by converged means, should I go on or not? Converged here means that the new coordination Ri is equal to or the same as the previous coordination, or it could be that the change in the energy, the gradient energy, could be equal to 0. I cannot go further in the negative direction. Or could also, what does it mean? It means that the new VRI minus the old VR is equal to 0. I'm not a change. So all of them mean the same thing, means converged. So if it's converged, yes, I stop. If it is not, I continue the process. And the bad news is, as far as I know, is the steepest descent will never ever converge into 0. But before you perform your simulation, you want to reach some stable or minimized structure of your minimize the state of your structure. Okay, this is the basic concept of the energy of the steepest descent, and let me know what you think about this explanation, and if you have any comments or corrections, because I'm learning with you. And wait the next video about some advanced stuff. Thank you.